Okay, once again, welcome folks to another series of problem solving on mechanics. For the problem here, where we have forces acting on an object. I mean, this object is experiencing equilibrium, but it's not a popular scenario that we have seen in previous questions. Let's try and have a look at how best we resolve whatever that's required. Okay, there we go. This time around, we have a force acting at an angle. And normally we have forces to the right-hand side of the object. But let's see how best we can play with this. See, uh, let's see if I can write here. Let's check. Okay, I have my pen here. Let's see now. Right, the best way of approaching this is to assume that this force is going to continue in this manner. Now, when we check carefully, it looks like these angles are alternating because, I mean, the surface and the force angle, they are parallel, so that will be 35 degrees, implying this will also be 35 degrees. So if we have that in mind, I think for the status will be fine. Now, reading through the problem, let's try and check what's required there. Particle of mass 0.6 kilograms is placed on a rough plane, which is inclined at an angle of 35 degrees to the horizontal. Now, the particle is kept in equilibrium by horizontal force of magnitude, P newtons. So it's important to have this force, P newtons, acting in a vertical plane containing a line of greatest slope. So we're looking at the diagram. Coefficient of friction between particle and the plane is 0.4. So we have our mu here. Find the least possible value of P. So if we want the least possible value, what we need to realize is this object has got its weight, and pulling it down the plane, we have W sine theta. But we are told that this plane is rough, so it implies there's friction. And friction is going to take a side which depends on the direction that the object is likely to move. You say it's in limiting equilibrium, it's about to move. So if it's about to go up, it means friction will be facing down the plane. If it's about to go down, it means friction will be facing upwards. So we want the least. So we only find the least if the force applied P, and for this case, it's going to be cos theta, will be in the same direction as friction. Then we have the least value of P. So having that in mind, let's try and see if we can reformulate the solution to the problem so that we can find the least possible value of P. So let me go down and redraft the problem. We are told that this is the scenario. We have 35 degrees. There is the object, and already we have noted that the force P is acting at 35 degrees. And this can be broken down into its components, horizontal and perpendicular. And we are told that the object's mass is 0.6, implying its weight is going to be 6 newtons. And when I break this into its components, I'll be having perpendicular and parallel. So what we know is the force pulling the object downwards is going to be 6 sine 35 degrees. And going up the plane, up the plane, up the plane we have 2. It's going to be P, we're interested in this component, so it's going to be cos 35 degrees. And this component here is actually P sine 35 degrees. And remember, we also have the weight component here, which is 6 cos 35 degrees. It's coming from the weight of the object. Then perpendicular to the plane, we have the normal or reaction force. So if we check carefully, it looks like for us to come up with with um, the value of P, like we agree that friction and the component of P will be facing the same direction. So we have F here. So if I'm to draw my equation below, I'm going to say, because the object is experiencing equilibrium, it means there's a balance. So if a balance between friction and P cos, well, it's going to be P cos 35. So P cos 35, this is going to be equal to 6 sine 35 degrees. And this is going to give us the least value of P, because friction and P, they are in the same direction. Then what do we do? Our challenge is on our friction. Because we know friction is mu r. So with friction here, which is given as mu r, what we know is mu, the coefficient from the problem, we're told is 0.4. So I'm going to say here 0.4 into r. But what's r? R, I'm going to calculate it above, because we know from our diagram here, let me change the color to red, to say r is equal to, it's a balance between these two forces. So it's going to be 6 cos 35 and P sine 35. So it gives us our there's no need to put brackets here, both they're independent. Right, so still moving, because we found our R, we can come below to say, but when we say R, back to our substitution, it's going to be 6 cos 35 degrees and P sine 35 degrees. Wow, this is going to be, well, there is a plus P here, P cos 35 degrees. This is equal to 6 sine 35 degrees. Then let's see if I can expand the brackets, because I want to combine the like terms. So on expanding the brackets, I've got 0.4 times 6, it gives me 2.4. So it's 2.4 cos 35 degrees. And there I'll be having, when I multiply this, that's 0.4 P sine 35 and plus P cos 35. This is equal to 6 sine 35 degrees. Well, if I look at this part, it looks like it doesn't have P with it. So I can easily transpose it to the other side. So I'll end up having that's 0.4 P sine 35 plus P cos 35 being equal to 6 sine 35. Then I'll subtract this part, which is minus 2.4 cos 35 degrees. Okay, proceeding with the problem, I'm going to factor out P, because P is common here. So if I factor out P inside the brackets, I'll be having 0.4 sine 35 and cos 35. We are saying this is equal to 6 sine 35 minus 2.4 cos 35. So to find our value of P, we'll divide both sides by what's inside the brackets, which is 0.4 sine 35 and cos 35 degrees. We'll also do it the other side, which is 0.4 sine 35 and cos 35 degrees. So here numerator and denominator are the same, so they will cancel. We end up having our P equal to, I'll need my calculator and try and do my substitutions there. Let me try and open brackets so that I don't miss. On the numerator, we're saying is 6 sine 35. There is minus 2.4 cos 35. Okay, that's my numerator, divided by, inside the brackets, I have 0.4 sine 35 plus cos 35. Let's try and check what we'll get there. Looks like the value of P is going to be 1.4, 1 to 2 decimal places. So it looks like our P is going to be 1.41 newtons. Right, I hope you guys will found this meaningful. We'll meet in the next part, which is graphs of motion, where we'll try and see how best we also find the mathematics behind displacement, velocity, acceleration, you name it. Thank you.